Okay, we have seen that an Euler path or an Euler circuit passes through every edge. In contrast, a Hamilton path or a Hamilton circuit is supposed to pass through every vertex exactly once. Okay, so you visit every vertex exactly once, and that defines a Hamilton path, or if it's a circuit, it's a Hamilton circuit. Now, we have seen that finding Euler paths or Euler circuits is not that difficult. We have linear time algorithms. On the other hand, finding a Hamilton path or a Hamilton circuit in a graph or showing that there exists none is NP complete. So it's considerably more difficult to deal with Hamilton paths and Hamilton circuits. Uh, and also, we have also seen that sufficient and necessary conditions are given by Euler for Euler paths and circuits. With Hamilton paths and circuits, that's not the case. We have some sufficient conditions for existence of Hamilton paths and circuits, especially for some special types of graphs, but no necessary conditions are known for arbitrary graphs. So if you don't have a special type of graph, determining whether it has a Hamilton path might be really, really difficult. Now, another concept regarding paths and cycles is what we call shortest paths, and this is related to weighted graphs in general. And this is the problem of finding a path whose total weight is minimized from a given initial vertex to a destination vertex in a weighted graph. Now, the graph could be directed or undirected, but for shortest path to make sense, it needs to be weighted. If you are just considered in the number of edges uh, in a shortest path, then you can define each edge with a weight of just one. For shortest paths in such graphs, we have a number of algorithms, but probably the most famous one is Dijkstra's shortest path algorithm, and it finds shortest paths from an initial vertex to all other vertices in general. And it's a greedy algorithm and a polynomial time algorithm. So this means shortest path problem is not really a very difficult problem in general. However, when you consider the minimum weight Hamilton circuit problem, that's a different story because the earlier problem is this one is different from one initial vertex to a destination vertex. Find the path so that the total weight of the path is minimized. But if you want your path to pass through every vertex, now that defines a minimum weight Hamilton circuit, and this is called the traveling salesman problem, TSP in short. And some of you might have heard of this. This is a very famous problem in computation theory and complexity theory because it's one of the earliest examples of NP-complete problems, which means there is a linear time, sorry, a polynomial time reduction from the traveling salesman problem to the Boolean satisfiability problem. And in fact, the traveling salesman problem can also be used as a benchmark where if you can reduce a given problem to the traveling salesman problem in polynomial time, you can in fact call that problem NP complete. So the traveling salesman problem in this context is a difficult problem because it forces you to pass through every vertex. And there are some approximate solutions which are maybe suboptimal, but quite close to optimum. So people have made progress towards the solution in a practical aspect, but in a theoretical point of view, it's not still not in P as of this point, and it remains as an NP complete problem. On the other hand, if you just consider one initial vertex and one destination, and you want to find a path from the initial vertex to the destination such that the total weight of the path is minimized, that is a considerably easier problem. And for instance, Dijkstra's shortest path algorithm can solve that in a linear time. And there are also some other algorithms that do this. But in the context of this course, we are going to study Dijkstra's shortest path algorithm next.